We did something which most people consider to be a bit of a heresy. We decided that the speed of light could change in space and time, and if that is true, then our perceptions of physics will change dramatically.
At the dawn of a new century, a new theory is being born. It threatens to demolish the foundations of 20th century physics. Its authors are two of the world's leading cosmologists. If they're right, Einstein was wrong. It all began when Andy Albrecht and João Magejo met at a conference in America in 1996.
This was a pretty exciting meeting in Princeton. Most of the key people were there. There was lots of debate about the contemporary issues in cosmology. João came up to me sort of late one evening, I think, just when I was ready to leave, I think, and had a very interesting idea.
This is total bullshit. It wasn't like that at all. It wasn't like that.
Well, it was late.
It wasn't like that.
How was it, João? How do you remember it?
Okay, let's start, shall we? The story as I remember it was, at least when I was present, was this conversation between the three of us. And then each one of us suggested something. And I remember I suggested a varying speed of light, and there was embarrassed silence. I think you two thought I was taking the piss at this point, because...
Maybe, possibly.
But then he's actually serious, he's not laughing. So, and then we took it from there, actually. We started taking it more seriously.
For most scientists, the idea that the speed of light can change is outrageous. It flatly contradicts Einstein's theories of space and time. But recently, astronomers have begun to realize that the universe doesn't always behave as his theories would lead you to expect.
We're making measurements which indicate that the universe is filled with some kind of energy density. We don't understand this energy at all. It's unlike anything else in physical theory.
And the surprise is that instead of the universe slowing down, in fact, it's speeding up.
It's certainly a very profound result for physics, because it would be the first ever indication that the laws of nature were not always the same as they are today.
Who knows what's in store? I think in some ways it's a very exciting time. It's very similar to the revolution that was seen in physics at the turn of the last century. So here we are, about to enter the new millennium, with a whole lot of uncertainties in store.
To understand what's at stake, we need to go back to that scientific revolution. It began here in Bern, Switzerland in 1905. As the new 20th century dawned, the intricate mechanism of 19th century physics was beginning to show signs of strain. It was finally demolished, not by an established scientist, but by a patent clerk.
When Einstein started his career, we still lived in a Newtonian clockwork universe. Space and time were simply a reference system. The meter was a meter. It was a meter anywhere you went. Time clicked at a constant rate throughout the whole universe. Second was the same. It was unaffected by where you were, whether you were moving.
Time was considered as an absolute concept. That time would be everywhere the same, independent of the state of motion of somebody. That there would exist an absolute time which could be measured with a clock like that one. This was probably the concept which Einstein kind of smashed with his new thoughts.
The tool that Einstein used to shatter the clockwork universe was the speed of light. He knew that for 20 years, scientists had been puzzled by an experiment which suggested there was something decidedly odd about the speed of light. In the 1880s, two American scientists, Albert Michelson and Edward Morley, set out to measure how the speed of light was affected by the Earth's motion through space. They set up an experiment with beams of light.
Well, in this experiment, there's a light source, which is the laser, and really what one's doing is splitting the laser beam into two, sending them in two directions at right angles, and measuring, in a sense, the relative speed of light along those two beams, and recombining them here, and the pattern that you see is the interference between the two beams, and it's measuring the relative speed of light within those two beams.
If the apparatus were static, there'd be no reason to expect a difference between the beams. But in fact, it's moving very fast indeed. Our planet orbits the Sun at 30 kilometers a second. It also spins around its axis once a day. So every laboratory on Earth is spinning through space.
Well, at this time of day, the Earth is essentially moving in this direction through space round the Sun. If we then waited 6 hours, the Earth would have turned, and then this direction would be the direction of motion of the Earth through space, and then in another 6 hours, this direction will be back but reversed. So that by doing nothing, you can just sit here and very, very smoothly the Earth takes you round, and then you can just look at the stability of your apparatus.
Michelson and Morley assumed that the planet's speed would add to the speed of the light beams in their apparatus. So they expected to see a regular pulsing of the pattern every 6 hours, as the Earth's motion added to the speed of light in first one beam and then the other.
The surprising thing, of course, was that the measurements showed that nothing happened. And no matter how they did it, when they did it, and whether they waited a long time, all year even, still nothing happened. And that's the beauty of the experiment, that if you can measure nothing very, very precisely, then you've got something really important.
The importance of this result was that it proved that you can never add to or subtract from the speed of light. This was a direct contradiction to what was supposed to happen in the clockwork universe. When space and time are fixed, speeds must always add up.
In such a world, one has a very simple rule for the addition of speed, the addition of velocities. In Einstein's example, if you're walking along a tram or a train, your speed with respect to the ground outside is just the sum of your speed walking along the tram and the tram speed with respect to the ground.
But the Michelson-Morley experiment had proved that this was not true for light. Light leaves the tram at the speed of light and strikes the pedestrians at the speed of light, and this speed never changes, no matter how fast the tram is going. But something must change as a result of the tram's speed. Einstein realized that it must be space and time themselves.
Once you assume that the speed of light is the fixed thing, this will imply that space and time can no longer be fixed, and that, for example, a moving clock, which is moving with respect to you, goes slower.
So viewed from the pavement, the speed of the light from a tram is not affected by its motion. Instead, the watches the passengers are wearing will run slow compared to a stationary clock. In a small two-room apartment a few yards from the clock tower, Einstein wrote up his radical theory of special relativity.
Advertisement of the unemployed Einstein offering.
Yeah, he offers private courses in mathematics and physics for students. I mean, for some time he was unemployed, right?
Oh, nobody wanted him. And they thought he was too lazy.
I think they thought he was too troublesome. Does it say there how much he charges, or do you have to call up and find out?
It says that there are test lessons for free.
Okay, I think I'll come by and have a test lesson. Just to see what it's like.
But Einstein's fortunes were about to change.
So here he is, 1905, 26.
Very penetrating gaze.
In that year, he published several papers, of which relativity was just one.
6 papers if you count the PhD dissertation, right?
In 1 year.
In 1 year.
And each one founds a field of physics.
And each one is worth a Nobel Prize.
I wonder if he realized just how big a change he was making to the world when he wrote that down.
That's the E equals MC squared paper, which he published very shortly after that one.
Look how thin it is.
Very thin.
Jeez. 3 pages. If I could trade all of my lifetime publications for these 3 pages.
But Einstein himself was not satisfied. The problem was that his theory of relativity broke down when gravity entered the picture, and gravity was the dominant force in the universe. Einstein realized that he had to take his notion of flexible space and time even further.
He had to give space-time actually properties. It was no longer just an empty place where things occur. It was something that actually was interacted with. So in his famous statement, mass tells space how to curve. The presence of mass actually curves space-time. And then the flip side of that, his next part of his statement, is space tells mass how to move. So a mass moving through space-time now just follows the curvature induced on it by the presence of a mass. And this solved an old problem from Newtonian mechanics. The Earth is going around the Sun. The Earth feels a gravitational attraction to the Sun. How does it do that? How does the Earth know the Sun is there? What is the source of this instantaneous action at a distance? In Einstein's model, there is no such instantaneous action at a distance. The mass of the Sun simply curves space-time, and then the Earth follows that curve. Just like this tram follows the tram line it is on and responds to the local curvature of the tracks. It doesn't know if those tracks are going to curve some distance in advance. It doesn't need to know. It just follows the local curvature of the track. Einstein realized that it wouldn't just be mass that would cause gravity. It wouldn't just be mass that curves space-time.
Every form of energy, like heat or also pressure, add to the gravitational field.
There's nuclear energy, there's just many, many different types of energy, and all of them cause space-time to curve the same amount, depending just on the total amount of energy present. Mass is nothing special in this regard.
For 10 years, Einstein searched for an equation to express this relationship between mass energy and space-time. In the end, it was stunningly simple. G equals 8 pi t. In 5 characters, the Einstein field equation encompasses the structure of the entire universe. It ranks as one of the supreme achievements of human thought.
When, as a student, you learn this theory, you find it extremely beautiful and simple. But then if you think, how did he get it? I mean, how on earth did he find out these equations? That's a miracle. I mean, still now you can't really understand how he got there.
But Einstein didn't stop. He set out to use his new equations to describe the entire universe. It was a bold leap, and immediately he ran into problems which still remain.
Relativity was a great success, at least until Einstein had the courage to apply relativity to the universe as a whole. And he invented cosmology, scientific cosmology. But at the same time, he gave us a lot of problems which are still with us. basically the universe as we see it doesn't want to be like that according to relativity.
Einstein's approach was based on a daring assumption. He knew that locally stars would distort space-time in complicated ways that would be too difficult to calculate. But he believed that if he stepped back far enough, all the matter in the universe would look like molecules in a cloud of gas. The cosmological fluid. From this perspective, the shape of space-time would be uniform and simple enough to deal with. But when he began to calculate how the universe would behave under the influence of gravity, he got a nasty shock.
You look out in the universe and you see what appears, if you just look up, what appears to be relatively stable, the unchanging stars. And in Einstein's era, they thought the universe was remarkably static. It looked the same over time. But in Einstein's solutions, this couldn't be true.
Einstein found that his equation predicted that all the matter and energy in the universe would fold space-time back upon itself. Soon the universe would meet a fiery end as all the stars and galaxies collapsed into an enormous fireball.
And in order to prevent this, Einstein had to add a term, which is called the cosmological constant.
To Einstein, this extra term, lambda, the cosmological constant, spoilt the beauty of his original equation. But he could see no other way to make the universe stable.
Now, this is a constant that gives space-time itself the property that it would tend to spontaneously expand. Okay? And so he added that constant in with just the right amount, that this property of space-time to expand would exactly balance the property of the matter in the galaxy, or in the universe, to collapse under its own gravity. And so by exactly balancing these two, he could therefore make the universe stable. Now, it wouldn't really have worked, of course, because it's the stability of a pencil on its point. Even the smallest deviation to too small a matter density, or too large a matter density, would have made the universe collapse or expand. So I don't really think he'd solve the problem.
Einstein's problem was that according to his theory, the universe was inherently unstable. It should have collapsed or exploded long ago. It's a mystery that worries scientists to this day. This is the echo of creation. Detune a television set and it will pick up microwave radiation from the edge of the visible universe. When it set out on its journey, it was orange light, but over the 15 billion years it has been traveling, the universe itself has grown 1,000-fold, stretching the light so that we now see it as microwaves. It warms us as it warms the entire cosmos, raising the temperature of space by 3 degrees. This signal is powerful evidence that the universe is not unchanging as Einstein imagined, but that everything we see around us was once part of an immense fireball. The first hints of that fiery beginning were found when astronomers started to look out into space beyond our own galaxy.
Well, the 1920s was an exciting time in astronomy because that's when the first large telescopes came online. And Edwin Hubble, an American astronomer, started looking at nearby stellar systems, which we now call galaxies.
Dr. Edwin Hubble, on a movable platform, lines up the massive telescope as he begins a cold night's work.
And to his astonishment, he found that they were very, very far away, firstly, and secondly, by measuring the light from these galaxies, he was able to see that they were moving away from us.
To Hubble, this could only mean one thing. The universe itself must be expanding.
It's a pretty profound discovery that the universe is expanding, because if you think about it, what that means is that at some point in the past things were closer together. And so if you measure density, so the number of galaxies in a little box of space, then as you go back in time, the number that fits in a fixed box of space goes up. And so the universe becomes much denser and hotter, and as one goes back in time, eventually you come to a point which we call the Big Bang, when the density was extremely high. And so the profundity of this discovery is that the universe had a beginning, a Big Bang.
If Hubble was right and the universe had started with a cosmic explosion, then the force of this alone might be enough to counterbalance gravity's tendency to make the universe collapse and die. Perhaps here was a way to make the universe stable and solve Einstein's problem.
So it's pretty interesting, actually. Einstein, you would have thought, would respond positively to observations, but as is often the case, theorists completely ignore observations. And so here was Hubble with a fantastic discovery, probably discovery of the century, and Einstein really didn't take any notice of it. So Einstein stuck to his static universe, insisted on his cosmological constant to keep the universe static, and it wasn't really until a meeting here in California between Hubble and Einstein in about 1932 that really there was a synergy between Einstein and the expanding universe.
And here he comes, down from the sun tower after a hard morning, looking a few million miles into his favorite space.
Hubble, in the middle here, soon convinced Einstein that the universe was indeed expanding. The cosmological constant, which Einstein had introduced to hold up a static universe against the force of gravity, appeared to be unnecessary after all. With relief, Einstein returned to the original form of his general theory of relativity.
And it's at that time, or shortly after, that Einstein said that the invention of this cosmological constant was his biggest blunder.
The construction was very skillful. You had to build up the outside, then put in the inside, then more outside, inside. It was a great piece of engineering.
But Einstein's optimism was premature. It has gradually dawned on cosmologists that the Big Bang doesn't, in fact, solve the problem of the universe's stability. For 21st century physicists like Zhao Mageju and Andy Albrecht, the cutting edge of research is still the problem first identified by Einstein back in 1916.
Assumption in which there is no sun. If you can really make that connection, then it's a reason why people should want the speed of light to vary. You'd think with all the great successes of the Big Bang, we'd be happy. We wouldn't be complaining. But we're concerned. There's a problem with the Big Bang, and the problem is we shouldn't be here.
The universe has been gently expanding for 15 billion years. That's allowed time for stars, planets, and cosmologists to evolve. The problem is, it's almost impossible to get a gently expanding universe out of the Big Bang. Either it expands too fast, or it falls back in on itself. Either way, the universe could not last very long.
A good analogy is to think about throwing a rock in the air. You throw it up, you expect it to come back after a little while. You throw a little bit harder, it goes further, but eventually comes back. If you throw it hard enough, and no human can do this, but NASA can do it with a spaceship, you can leave the gravitational attraction of the Earth and fly off forever. With the universe, there's this delicate balance. You throw the rock in the air, it keeps going. Is it going to turn around? You don't know. It keeps going, it keeps going. You don't see it flying off, you don't see it turning around. It's balanced right at the edge for year after year, thousands of years, billions of years. We're now at almost 15 billion years, and we still don't know, is it coming back? Is it flying off? That's what the universe is like.
With the ball, it's how fast you throw it. With the universe, the key thing is the amount of matter and energy in the Big Bang. To produce gentle expansion, the density of this energy has to be precisely right.
How do we start this universe out in such a special state? We have to take a number that describes the density of the matter in the universe and get it right to 100 decimal places, one after the other. If we get one decimal place wrong, the whole thing gets out of whack. No physicist can stomach setting up a universe in such a delicate way.
Yet something set up the universe in the right way. Some mysterious process made sure that matter and energy had everywhere the same critical density, keeping the entire cosmos in perfect balance. Scientists call this the flatness problem.
So this is the flatness problem. It's the fact that the universe is a bit like a pencil standing on its tip for 15 billion years.
And it's even worse than that.
The puzzle is that when you start saying, okay, suppose at the beginning things were different and something could come along and adjust everything just the way you need it, you run into the following problem. Nothing can travel faster than the speed of light.
The universe is very, very big. Bigger than we can imagine, and bigger than we can see. There are regions of space so far away they are invisible, because the light from them has not yet had time to reach us. In effect, we are surrounded by a horizon. This horizon has been growing at the speed of light since the universe began, but beyond it are regions with which we have never had any kind of contact. Since nothing, not energy nor any kind of physical process, can travel faster than light, nothing can cross the horizon.
The universe is now 15 billion years old, which means that the horizon is actually very large nowadays. It's about 30 billion light years across. This doesn't mean that the universe is only this size. Of course, the universe is infinite. It just means the region we can see is this 30 billion light year region. Okay? And when the universe is very young, conversely, it's still very big, but conversely, you see a smaller and smaller fraction because the horizon is smaller and smaller.
To see what this means, imagine that we could travel back in time. We would see the universe shrinking rather than expanding. But our view of it would shrink even faster because our horizon would be shrinking at the fastest possible speed, the speed of light. Galaxies that are visible today would have been invisible to us in the past, and to each other. So the early universe was divided up into small islands, isolated inside their own small horizons. This picture of a disconnected universe flies directly in the face of the idea of a single balancing process needed to solve the flatness problem. Confused? So were the cosmologists. The only way round this horizon problem was to assume that the entire region we see today started out so tiny it could fit inside a single horizon. This idea, called inflation, was first proposed by Alan Guth and then developed by Paul Steinhardt and his colleague Andy Albrecht. Today, their version of inflation is widely accepted among scientists. But Andy Albrecht himself has never been wholly convinced by his own theory.
So what we have to do to make inflation work is invent an entirely new form of matter that exists in the early universe and then disappears so we don't have it around today. And I was always left with a nagging feeling that if you invent so much, is inflation really the right thing to invent, or could nature have chosen something else?
As a young researcher at Cambridge in the mid-1990s, João Magejo was also skeptical about inflation.
I mean, because inflation is the only thing available, people cling to it just like to a lifeboat, and there is this feeling.
But some people need it. That's great.
Well, a bit extreme, you could say. You could solve all these fine-tuning problems using divine intervention. And I think inflation is a scientifically acceptable way to invoke divine intervention.
Okay, well, I think that's a bit over the top, but there's enough open questions that we really need to think about it.
One day, João saw that there might be a much simpler way to solve the horizon problem.
So one winter morning, like this one, and walking on these fields, I just realized that if you were to break one single but sacred rule of the game, the constancy of the speed of light, you could actually solve the horizon problem. And when you think back at it, it's just such an obvious thing that when the universe is very young, if the light was very fast, you could actually have a very large horizon. When the universe was 1 year old, the horizon would be one quick light here across, which could be as big as you wanted. And of course, you connect the whole of the universe if you do this.
If early light was much faster, a single horizon could be big enough to encompass the entire known universe. It was a bold idea. Too bold.
Well, this came at a time when I was a fellow of this college, but it was also a stage in my career where I had to look for a job. I was about to finish my position here, so this is not the time to go and pursue a very original idea. I was already quite controversial at the time. I didn't need one thing which would be even more controversial. Certainly there were times when I saw myself selling the big issue outside St. John's College. So I waited until I was on a much safer ground.
João found that safer ground when the Royal Society awarded him a rare and prestigious research fellowship. He joined Andy Albrecht's group at Imperial College. They started to work on João's idea together.
There we go. My mother sees me smoking, she kills me. One day Andy just called me to his office and he said, João, let's work on the varying speed of light here. And he closed the door, he made a big secret about it. He erased the blackboard afterwards. He was really afraid someone might steal the idea. And then gradually we just started putting more and more maths together, try and find more and more things about the theory.
C is very, it's not very You face the frontier, you face unknown questions, and you argue about it, and you have competing ideas, and after a while, one is clearly the winner.
When you're really worried about something, it really is with you all the time, not just in your office. You go through phases in which you dream about your ideas, you sleep over your ideas, you wake up tired. Well, you need to cast things into equations in the end, because this is what science is all about. It's about mathematical models, not just pictures. Otherwise, it's all very cranky. I think there is a very unique aspect of scientific discovery. There is a big adrenaline rush when you've spent months and months struggling with a problem, getting it wrong, and eventually you discover something, and it's unique. I'm addicted to adrenaline in general, but this one is unique. And I think this is the reason why scientists tend to be such big nerds, because social interaction, for instance, doesn't match quite this kind of pleasure which scientific discovery can give you.
João and Andy were creating a completely new physics. As they explored this strange new world, it began to dawn that perhaps they could solve more than just the horizon problem.
Well, then we got more than what we bargained for, and this is really where the thing was massively rewarding. We found that we could solve the flatness problem as well. And the reason for that is we realized very quickly there's no way we can have energy conservation if the speed of light varies.
In conventional physics, energy is conserved. It can be transformed, but it cannot be created or destroyed. This is the principle of the conservation of energy, and it means that the total amount of energy in the universe is fixed. So the critical energy density the universe needs must be established perfectly, right from the beginning.
Now, if you change something as fundamental as the speed of light, which is woven into the whole fabric of physics, then of course you're breaking that principle. The universe is different at different times, and you don't conserve energy. But then you realize this is exactly what you need to solve the flatness problem, because you violate energy conservation, pushing the universe to the critical energy density. That is, you create energy if you have a subcritical energy density, and vice versa. You take away energy if you have a surplus of energy density.
In their theory, during the early universe, the speed of light was falling, which allowed the cosmos a built-in thermostat, creating or destroying energy so that the critical density was maintained exactly. Thus, the universe remained in balance for billions of years.
We were just trying to find an alternative to inflation as far as the horizon problem was concerned. We actually did not have hopes of solving everything. This was a gift we got out of it.
João and Andy had set out to solve the horizon problem and stumbled upon a theory that solved the puzzle which had plagued cosmology since the time of Einstein. They had made a universe that was inherently stable, held in balance by the creation or destruction of energy. A theory which predicted the universe as we see it today. However, it was still just a theory. Proof could only come from the depths of space-time. But what astronomers found there would astonish everyone, suggesting that the speed of light was also the key to the biggest mystery in cosmology. What happened before the Big Bang? Long ago, when the universe was young, light itself travelled faster than it does today. The laws of physics were very different. That, at least, was the theory. The evidence could only come from the world's great telescopes. As they scan the far depths of space, astronomers also look back in time. In 1998, the British astronomer John Webb started to become interested in the question of whether the fundamental constants of nature could change as the universe evolves.
We're using a technique which enables us to look back into the past to measure physics as it was a long time ago. So we're doing that using quasars.
Quasars are the most distant objects we can see. They are thought to be primitive galaxies in the process of formation. But John Webb is not interested in the quasars themselves.
Quasars are just, as far as we're concerned for this study, very distant sources of light which shine through the universe to us. In doing so, they intersect gas clouds along the line of sight, and then we can study the physics of those gas clouds by looking at the way in which the light is absorbed. We can look at gas clouds relatively nearby, and we can look at them just about as far away as the most distant quasar. That means, in terms of look-back time, almost 10 billion years or something like that, an awful long time ago. So we're studying physics as it was when the universe was quite young.
When light passes through an interstellar gas cloud, it collides with electrons in the gas molecules. This creates a pattern of dark lines in its spectrum. What John Webb noticed was that this pattern looked different in the spectra from the most distant clouds. The inference was astonishing. Either the electrons were different, or the speed of light was greater in the distant past.
If it's correct, it's certainly a very profound result for physics, because it would be the first ever indication that the laws of nature were not always the same as they are today.
But far off in space and time, an even more amazing discovery was waiting for astronomers. Today, cosmology is buzzing with news of the unexpected comeback of an idea discarded 70 years ago: Einstein's cosmological constant, lambda. For João, it means taking his theory even further. He now believes the cosmological constant could be the link that connects changes in the speed of light to the origin of the universe itself.
So Einstein had already endowed space-time with its own life when it allowed space-time to curve, to have its own dynamics. And the cosmological constant was one step further. It was basically giving space-time its own energy, so that even before you put matter into space-time, when you have vacuum, you have some energy density in this vacuum. And this is what lambda is. It has this very interesting property that essentially it makes repulsive gravity.
Lambda produces gravity that pushes things apart rather than pulling them together. And that seems to be what's happening to the universe. Something is blowing it apart. Ever since Hubble convinced Einstein that the universe is growing, astronomers have been trying to measure its rate of expansion. The breakthrough came when they started to concentrate on exploding stars called supernovae. They thought that these would allow them to chart the gentle deceleration of the universe. What they actually found was precisely the reverse.
Now the question is the universe slowing down, as we would expect? And the surprise is that instead of the universe slowing down, in fact, it's speeding up.
Something is upsetting the delicate balance of the universe, pushing the galaxies apart faster and faster. A new force in the vacuum of space.
The acceleration that is seen from the supernova data, of course, raises the amazing question of resurrecting Einstein's cosmological constant.
It looks as if space-time is humming with energy. Buried in the equations of his theory, João has found a hidden link between this energy and the speed of light.
Well, at some point we found that two interesting things. One was that the energy in the cosmological constant also depends on the speed of light. And in particular, if the speed of light drops, then the energy in the vacuum drops as well. And the second thing we found is that this cosmological constant itself promotes changes in the speed of light. It can make it drop in value. So you have an instability.
In João's theory, a change in the vacuum can cause a drop in the speed of light. But this in turn reduces the amount of energy the vacuum can hold, forcing energy out of it and into ordinary matter and radiation. Could this be the genesis of the universe? What happened before the Big Bang?
So in some of these scenarios in the beginning, there is just a vacuum, but the vacuum is not nothing. It's actually the cosmological constant, this pool of energy in the vacuum. And in these theories, then, it is this energy what drives changes in the speed of light. It makes it drop in value. And what that does, that makes all the energy in the cosmological constant drop as well. It has to go somewhere. Where does it go? It goes into all the matter of the universe. So it causes a Big Bang. So in these scenarios, it's actually this sudden drop in the speed of light, this change in the speed of light, what causes the Big Bang.
In the beginning was the void. But the void was not nothing. And there was light, and the light changed. And so the void brought forth the world. And the world was good, for it endured until men could comprehend it. But it will come to pass that one day the energy of the void will have pushed all things away, leaving nothing but the void. But the void is not nothing.
And you might think this is the end of the universe, but of course, in the picture of this theory, it's just creating the conditions for another Big Bang to happen again. Another sudden drop in the speed of light, another sudden discharge of all this energy into another Big Bang. So it is possible that actually our Big Bang is just one of many yet to come, basically, and one of many which there were in the past already. And maybe the universe is just this sequence of Big Bangs all the time.
João's bold challenge to the constancy of the speed of light has led him to a wholly new view of the cosmos, one in which the universe no longer has a beginning and an end, but is eternal, an endless cycle of Big Bangs drawn from the vast reservoir of energy in the vacuum. And like every cosmologist before him, João has been guided by the theory that started it all. It is a measure of Einstein's genius that even when he was wrong, somehow he was right. What he called his biggest blunder may yet prove his greatest legacy.
Well, of course, I respect relativity enormously, and I have this feeling that it is only now that I contradicted relativity that I really understand it. And it's actually just because I've gone against it that I'm showing my full respect to the great man. This is not at all trying to contradict Einstein or anything, it's just trying to take things one step further. Eventually, of course, it will be nature what will decide whether this is true or not. And I'm working on basically trying to find ways of deciding whether the theory is right or wrong. Some kind of experiment which will decide conclusively whether the varying speed of light theory is pure nonsense or not.
More Equinox next Monday at 9. Don't forget, João Maguejo will be at chat.channel4.com to answer your questions. Log on now. 2 Channel 4 books, The Earth and Warfare, are available from bookshops, priced $12.99 each. You can order your copy from the Channel 4 shop with free delivery on 08701234344. And for more information about tonight's programme, go to the website at channel4.com/Equinox.